Hello, college algebra students. This is Mr. Ainsberg. I wanted to make a partial answer key over the 9.1 worksheet, but I'm going to do it as a video instead so you can hear the explanations while seeing the work in case you're struggling with this concept of probability. So we'll do some of the problems on it, and it should lead you to figure out the rest on your own. So problem 1 says, make a probability area model using the table below to represent the two six-sided dice being rolled. Well, I'm rolling two six-sided dice. So you see how I have the top labeled the first dice and the second side labeled the second dice. I'm going to put all the possible outcomes on the top as headers. So I have, 1 can be an outcome, 2 can be an outcome, 3 can be an outcome, so can 4, 5, and 6. And below that, I'm going to write the probability for each outcome. Since it's a fair six-sided die, probability of a 1 is 1 out of 6. Probability of a 2 is 1 out of 6. A 3, I have a 1 out of 6 chance of getting any of those numbers when I roll a die. And it's going to be the same thing for the second die, because the second die is a fair six-sided die as well, which means all outcomes have an equal chance of 1 out of 6. So if you wanted to find the probability of each outcome, and I'll just quickly, it's not one of the questions, but if I want to know what's the probability of rolling a 2 and the probability on the first dice and the probability of rolling a 4 on the second dice, I would multiply the 1/6 times this 1/6 and get 1 over 36 here. That's how the area model works. But that's not what our problem asks. What our problem asks we'll look at part A, is find the probability of rolling a 4 on the second dice. And remember, this vertical bar means given that a 5 was rolled on the first one. So I'm going to use some coloring for this to kind of help out. So given that is what occurred first. So assuming I rolled a 5 on the first die, that means this column, this event happened. My job now is to find what is the second event. Well, given that that purple happened, what's the probability of rolling a 4 on the second dice? Well, here's a 4 on the second dice. Now, if I take a look at that, that means I want to find the overlapping of this yellow event and this purple event. And I want to know what's the probability in that area. Well, that would be 1 over 6 times 1 over 6, and I would have 1 over 36 here. That's the first part. You're looking at, given that 5 is rolled, you see that purple column. What's the probability of 4? That's that yellow row. You're looking for the intersection of those. So that's part A. Now, if I look at part B, and part B will help you with part C. So I'm going to do part B, in which I'm going to have to erase these. So you could pause if you want to go back and take a look at those on it. And so if I'm looking at this, it says in a standard casino game, the roller wins on the first roll if he rolls a sum of 7 or 11. What is the probability of winning on the first roll? Well, this is interesting because there is no 7 or 11 on the dice, but the key phrase here is it says a sum of 7 or 11. So let's focus primarily. So I want to find the probability of a sum of 7 plus the probability of a sum of 11. Now, if we look at the notes for this, remember this is an OR. And that idea is you're going to find the probability of event 1. I'll call it event A. You're going to find the probability of event B, and you're going to subtract any overlapping. Now, there is going to be no overlapping in this case because you cannot have a sum of 7 that also equals 11. So I can't have two numbers that add to 7 and at the same time they add to 11. So there's no overlapping. So if I want to look at this, I have to find out what numbers add to 7. And we'll do that, and I will look at that as, we'll go purple. So what numbers add to 7 if I roll my die? Well, 1, if you look at the first column, plus 6 is 7. 2 plus 5 is 7. 3 plus 4 is 7. 4 plus 3 is 7. 5 plus 2 is 7. 6 plus 1 is 7. There's all my 7s on it. And what I'm going to do is I'm going to remove the 7s and I'm going to just highlight them to show you that this diagonal right here is the ones that add to 7. And I'm going to write down the probability. Remember, it's an area model. We're going to just do 1/6 times 1/6. This is 1 over 36. This is 1 over 36. This is 1 over 36, and so on and so on. Well, how many 1 over 36s do I have that add up to 7? And there's 6 of them. So the probability of a sum of 7 is 6 over 36. And I'm just going to leave that as is right now. I'm not going to simplify yet. Then it says find the probability of a sum of 11. And so the sum of 11 we'll do in pink. What numbers add to 11? Well, the 5 plus 6 is 11, and 6 plus 5 is 11. There's only 2 of them there that add to 11. And I'm going to do the same thing. I'm going to remove the 11s, and I'm going to highlight them in pink to show these are the 2 that add to 11. And I'm going to find the probability. Well, this one would be 1/6 times 1/6, and this would be 1/6 times 1/6. So there's 2 of them. There are no overlapping, and even visually you can see I didn't have any of the colors overlap. The purple is its own diagonal, the pink is its own diagonal. They don't overlap in any way. So I don't have this issue to worry about, as I said at the beginning. So I have 8 over 36, but always simplify your fractions. So I divide everything by 2, and I get 4 over 18. I can even simplify that, and I'm going to get 2/9. And that's your final answer, the 2/9. Always simplify the fractions for it. Now this will help you with part C, because part C is the same idea, except for now you're being asked, well, you're told that they lose if they roll a 2, 3, or a 12. So just like how I did with the 7 and the 11, you're going to want to do that with a 2, adding to a sum of 2, adding to a sum of 3, and adding to a sum of 12. So you should be able to do part C from this one. Now, if we look at number 2, in a certain town, 45% of the population has dimples and 70% has a widow's peak. So what I'm going to do, and I didn't do this at the beginning, so I'll do it now, is we'll label this top part as having dimples. And we'll say, yes, they do, no, they do not. We'll label the side as having a widow's peak. And we'll make this a yes, and we'll make this a no. So that's how we're going to label the outside for our area model. Assuming these physical traits are independently distributed, what is the probability that a randomly selected person has both dimples and a widow's peak? Okay, so now we're going to use some information given to us in the problem. We are told that 45% of the population has dimples. So if I were to think about that, yes, they have dimples would be 45% right here. So what I'm going to do is I'm going to write 0.45 right here. Well, if 45% have dimples, what percent don't have dimples? And that would be 55%. Because 100% minus 45% would equal 55%. So that's where I'm getting the 55 from. You're told that 70% have a widow's peak. That would be right here. Yes, they have a widow's peak. And I'm going to put a point. Now, you could just write it as 0.7. I'm going to write it as 0.7D. So then what percent don't have a widow's peak? Well, that would be 0.30. That would be 30%. And it's the same idea. I would do 1 minus 0.7, and that does not have it. So I have the outsides just like I did in number 1. I just had to kind of read what was given to me. Well, if I want to find, and I'm just going to forget about the whole questions, I'm going to fill in the rest of the area model for it. So I'm going to do 0.45 times 0.70, and I'm going to get 0.315 here. If I go to the top right, I'm going to do 0.55 times 0.7, and I'm going to get 0.385 here. I'm going to do 0.3 times 0.45, and that's going to give me 0.135 here. I'm going to do 0.3 times 0.55, and that's going to give me 0.165 here. And so there is our area model on this, our probability area model. And if I wanted to, I could add all those numbers together and I could check, and they do all add to 1 if I look at that. Now, what does this represent? This represents the idea of what's the intersection. So if I want to kind of look at, and I'll circle it before we do a problem, let's just do this right here. Let's look at this 0.385. What does that represent? Well, that represents somebody who has no dimples, but does have a widow's peak. That's the probability of that occurring is a 0.385, 38.5%. So each box represents a certain event. If I go right here, well, that's the probability of somebody who does not have widow's peak, but they do have dimples. So that's how you read the area on it. So I'm saying that to kind of help us with the problem. If I wanted to know, and I'll look at part B, what is the probability that a randomly selected person will have neither? Well, that means we want to find the probability of no dimples. Well, what is that going to look like? Well, if I want no dimples, I'm right here. But it's also the probability. So I have no dimples and they have no widow's peak. I want the probability that he or she will have neither, no dimples and no widow's peak. Well, that's the intersection. That's the overlapping of those on it. And so that would be this value right here. The probability of no dimples and no widow's peak in this case is going to be 0.165. And that's where we learned in the notes that and means intersection and uses this symbol right here on it. If you imagine just kind of drawing a horizontal line there, there's an A for and on it. But that's really what you're looking at, is you're looking at the probability of someone who does not have dimples and does not have a widow's peak. Now that should help you with part A, because part A says, hey, they have both dimples and a widow's peak. So they have both. So you should be able to figure that one out. Now, I'm going to kind of give you the setup for part C visually and have you go through it. Now, part C is what is probability that he or she will have dimples. So I want the probability of dimples, but not a widow's peak. So I want the probability that they have dimples. So yes, dimples, but no widow's peak. So and no widow's peak. So that allows us to see where we should highlight. I should highlight the yes dimples column, and I should highlight the no widow's peak row, and I should look for the intersection of them on it. So that can kind of help you with part C and part A for these problems. Now let's look at the part 2, which is tree diagrams on it. if we were to look at this one, it talks about the 4 pairs of pants. You have black, peach, gray, and cream, and you have 5 shirts on it. Draw a tree diagram to represent this situation. So I'm gonna have to probably zoom in and give myself a lot of workspace. So the way tree diagram works is we start off here and we branch off to the first event. And so we look at the first event, and we can look at it as event A. And this event A is the types of pants. And there are 4 types of pants. And so if we think about that as a probability, if I were to think about this, you have a 1 out of 4 chance of grabbing a gray pair of pants or a black pair of pants. So I'm going to break off and I'm going to have 4 branches. 1, 2, 3, 4 that lead off to event A. And I'm going to write down, here is the black, here is the peach, here is the gray, and here is the cream. And we have a 1 out of 4 chance of grabbing any one of those colors on it. It's equal opportunity for this one. So 1 out of 4, 1 out of 4, and I'm going to write the probability on the branch itself. There are 5 shirts: white, red, teal, black, and lavender. And so that's event B. So I have to branch off to event B, which event B deals with the shirts. So off of each of these, I'm going to have 5 branches. So the hard part about tree diagrams is you always run out of space. So we'll make it a little bit smaller. Here we go. Let's see if this works. So I have 1, 2, 3, 4, 5. And that's white, red, teal, black, lavender. I'm going to do W for white, R for red, T for teal, B for black, and L for lavender. Make it a little bit easier. And we have a 1 out of 5 chance. So I'm going to put a 1/5, a 1/5, a 1/5, a 1/5. Now that's pretty small writing, but we can still deal with it on it. And so here is what I have so far. And what I'm going to do is, because I have this ability, I am going to just take it and duplicate it with all of my branches. And you can see how easy it is to run out of room on a tree diagram. So I can slide that one down, slide the cream down. And there you go. So, wow, really, really, really big tree diagram. How many outfits does she own? So how many total branches do I have at the end? Well, I have 5 branches here, I have 5 branches here, I have 5 branches here, I have 5 branches here. There are 20 total outfits. Now, this is called, if you don't remember from the video, it's called the fundamental counting principle. If we take the number of outcomes from event A, which is pants, and there are 4 outcomes, and we take the number of outcomes from event B, which is the shirts, which are 5 outcomes, and we multiply those together, that will tell you the total number of outfits on it. Now, the closet light is burned out, so when trying to select a pair of pants and a shirt, what's the probability that she will wear something black? Now notice, probability of wearing something black. It doesn't tell you if it's the shirt or if it's the pants. So I want to find the probability of wearing black pants plus the probability of wearing black shirt. However, she does own a black shirt and she does own a black pair of pants. So I want to find the probability of the overlap, the probability of both being black, and subtract it. So whenever you're doing an OR, you always look at that minus the overlap on them. So the probability of wearing a black pair of pants is 25%. It's 1 out of 4. If I were to follow this along, so here's my black, I have a 1/4 chance of wearing something black. That's going to cover all of these. Ba-boom, 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 ba-boom on it. That 1/4 covers that whole outcome after it. So I have a 1/4 chance of wearing something with a black pair of pants. What about a black shirt? Well, a black shirt is a little bit different. A black shirt would be, and I'll start on the bottom for this one. It would be if I had a cream colored pants, I could wear a black shirt on it. So I could have a cream with a black shirt. That would be 1/4 times 1/5, which I'm just going to go to decimals for these. And so if I have 1/4 times 1/5, that's 0.05. So let's make our life a little bit easier. Let's change 1/4 to 0.25. But I could also have a gray pair of pants with a black shirt. That too. So a gray pair of pants with a black shirt would be 1/4 times 1/5, which is 0.05. I could also have a peach pair of pants with a black shirt. Again, 1/4. So peach pair of pants with a black shirt is 1/4 times 1/5, 0.05. I could also have a black pair of pants with a black shirt. So black on black clothing, 1/4 times 1/5, 0.05. But notice something. So the probability of a black shirt would be I have 0.05 plus 0.05 plus 0.05 plus 0.05. So I have plus 0.20. But do you see what happened right here? You can see my pink and my yellow overlap and my pink and my yellow overlap. I counted this twice. So I have to subtract that overlap. And so the probability would be 0.40. And so this is the same idea. Now, what is nicer on this, and I'm going to get you started with at least the tree diagram before, and you can figure it out for parts A and part B, is I would make an outcome table for it. I would say, so flipping a penny, a nickel, and a dime. And I'm going to try and make sure I have enough room. So here it is right here. We'll make that one penny. So I have a heads when I flip a penny, or I have a tails. So that is the first event. And I'm going to change these colors. Let's make it blue. Then I have next flipping a nickel. So I should have 2 more branches coming off. I should have a branch here and a branch here. And we'll do the nickel in green. Can have a heads and a tails. And I have the same idea for the next one. I could have a heads and a tails here. But then I have the third thing, which is flipping a dime. And so what I'm going to do is I can take this, duplicate it. Here's my heads and my tails. And I'll change the colors. We'll make this one red. And I have this for each of those, which is really 4 of them. So I'm trying to get it so I have room here. So I have a heads and a tails here. I can have a heads and a tails here. Again, give myself some room, slide this down. And then this could also repeat down here. So here is my tree diagram, which you can see it gets to be very, very, very big the more events you have. So that's to make a outcome table for it. And so if I look at my outcomes, I can have a heads, and a heads. I can have a heads, and a tails. And so what I'm doing is I'm tracing out, I can have a heads, a tails, and a heads. Or I can have a heads, a tails, and a tails on it. So all I did was trace out my events: heads, 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 tails, heads, tails, heads, heads, tails, tails. And I could do it for the next one. I can come down here and I can get a tails to a heads to a heads. I can keep tracing out the other ones. I have a tails, a heads, and a tails. Or I can take this path, tails, tails, heads. Or I can take this path, tails, tails, tails. So those are my outcomes on it. So I see it's organized. It's gonna be easier for me to answer all my probability questions for there. It even tell me how many outcomes I have. It answers part A for me just by counting them. But the reason why I say to do this is because we can count our probability faster. You have a 50-50 chance of flipping the heads or flipping the tails. And so I can label each of these with their corresponding probability. And that will allow me to generate my probability of each outcome, which will help me with answering my questions. So it's a little time consuming in the beginning, but you'll be able to answer your problems a little bit better at the end. So here we go, is heads, heads, heads is going to be, and I wish I could color code, it's just gonna take too much clicking on it, but I would do 0.5, and I would multiply that by 0.5, and I would multiply that by, well, 0.5. And so that would give me a 0.125 chance. What about heads, heads, tails? 0.5 times 0.5 times 0.5. Well, that's interesting. It looks like all of my paths are 0.5 times 0.5 times 0.5. So, I mean, I could keep doing this. Oh, it's a 0.5 times a 0.5. Should have been green. Times a 0.5. Okay, that equals 0.125. But all my paths, and I could just trace them out. 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5. They're all 0.5 times 0.5 times 0.5 on it. And so what I'm going to do is I'm going to realize all of these values are 0.125. And that allows me to calculate my probabilities for it. So I can count my total outcomes for part A. Now part B, I want to give you a heads up. It's something you have to just think about for a minute. Is the first one's not bad, 3 heads, so you just find this outcome. But when I say 1 head and 2 tails, I do not give the order. So you need to look at all outcomes that have 1 H and 2 T's. And it doesn't matter the order they are in. So I could have heads, tails, tails. I could have tails, heads, tail. Like you get the idea that it doesn't matter what order the 2 T's and the H are in. I can keep changing it up. That's what this is looking for. And even for part 3, at least 1 tail. That means you can have 1 tail, any order. You can have 2 tails, any order, or you can have 3 tails. well, I could say any order, but there's only one way to get 3 tails, and that's tails, tails, tails on it. So I can look at my outcomes and I can see, and we'll go yellow. We'll go blue. We'll look at blue as being 1 tail. And I can just look at my outcomes because I mean, look at this. I have right here 1 tail, 1 tail. I can keep going down. Here's 1 tail. I think that's all of the ones that are 1 tails. I can actually count. So I have 3 times the 0.125. I have 3 0.125s. What's the probability of, let's see, at least 1 tail? I got 1 tail. That's check. How about I look at 2 tails? We'll do green for this one. So we're looking at the probability of 2 tails. Well, in this case, 2 tails, I can just count. This has 2 tails. Let's see, this has 2 tails. This has 2 tails. Looks like I have 3 of them. And then I want the probability of 3 tails. And we'll do pink for that one, the probability of 3 tails. Well, there's only one way for that outcome to work. It's right here. It's boom, 3 tails, and that's 0.125. So I can add all those numbers together. So I could take my 0.375, 3 times 0.125, plus my 0.375, 3 times 0.125, plus that 0.125. And in that case, I'm going to get 0.875. There was no overlapping. You could see that by taking my time. I didn't have any of the colors overlap when I boxed in the outcomes. And that's how you go through. This all should help you with number 5. Number 5, it doesn't matter if you use a tree diagram or an area model, it's whichever one you are more confident with for it. So there is kind of a partial answer key to your 9.1 worksheet. Hopefully it helps you along the way. If you have any questions, please come off.